Hi guys, this is Ben, and I'm about to do a P3 replay of P319. This is strategies for solving mechanisms. I actually tried to do it during my discussion, but had a little difficulty getting in to the P3, so I only got to glimpse it really quick, but I hope that I'll be able to try it out now and really look at it. So, read the problem. Lewis acids, such as aluminum methyl dichloride, contain low-lying, empty atomic orbitals. Treating the starting material in Figure 1 with a Lewis acid leads to an interesting cyclization reaction. In Figure 2, an early intermediate is provided for you. Complete the mechanism of the reaction in Figure 1, provide all curved arrows and intermediates, but do not worry about stereochemistry. If you need more room to draw the mechanism, click View Sketcher window. I already do that. So, Lewis acids, such as aluminum methyl dichloride, contain low-lying atomic orbitals. This is going to lead to an interesting cyclization reaction. So, open my Sketcher window. Alright. How do I zoom in? Zoom. Here we go. Okay. I am going to the first step is an addition of a nucleophile and an association of an electrophile. So we only have one molecule. It all has to be intramolecular. So addition of a nucleophile is a pi bond to pi star in a sigma fashion, or it can be a lone pair to pi star in a sigma fashion. Usually, as you remembered, we use carbonyls for this kind of a reaction, so this is really good idea for what our attacking point is going to be. Now we find our nucleophile. We have a pi bond over here, which is an electron dense area. It's probably going to be a good nucleophile, so I'm going to say that's my first, and this is a cyclization, so I want to make a ring. I want to make the most stable ring I can make, and also I want to make something that is related to the products. And as we see, this is a 5-member ring, and so I want to make a 5-member ring with this step. We have 1, 2, 3, 4, 5 with this. So that's our 5-member ring, and these will get bumped up onto oxygen, relieving it of that positive charge. And so this is our association of an electrophile, essentially. And so copy this. Now move stuff around so that's a little nicer to look at. Dang it. Come on, yep, there. Okay, and then get rid of this bond. Why does it do that? Okay, get rid of that bond, create a bond here, which gets rid of that bond, and then, because that's what it was, right? Yep. And so, not what I wanted to do. There we go. And that makes this carbon right here positively charged. And so now, clean this up a little bit. Now we have a 1R rearrangement, or sorry, a 1,2 rearrangement. So it's moving over one bond. We need to get this carbocation right here next to this oxygen at this little center, plus we need to get our methyl group attached to our ethyl group on the ring. So I'm going to want to bring this guy here, switch spots, and I have 1-2 rearrangement steps. So I'll be able to get there through quite the journey. I'm going to first say that this is a charged species. It's going to want to be relieved first. Well, and it's the only way you can really do it, I guess. Make that a hydrogen. So there's a hydrogen right there at that stereo center, and then we have creates a bond. I bet it's not gonna like that, so I'm gonna move this there. Creates a bond. Copy that. And now erase that. Take off the charge, because now our hydrogen is down there, which gets rid of the charge, and add a positive charge to this center. Now, a 1-2 rearrangement usually involves a hydrogen, a hydride, moving over to a carbocation, or a methyl group moving over to a carbocation. So this is a really good spot to do our second one, and it gives us the product. So I'm going to move this here, move that guy down, and we use the electrons from our methyl, and that connects, and that should be it. That gives a carbocation right there. And I actually just remembered I need to get rid of these negative charges, and I want to erase this. So erase these, get rid of that positive charge. I'm sorry, I said negative, I think. Alright, so check the electron flow arrows really quick. We have our pi moving over, addition of a nucleophile, which sends that up there, and that's where the electron flow stops. That becomes a carbocation, which is where we have our carbocation right here. That looks good. So now this step, we have a 1-2 rearrangement. This hydrogen, the electrons flow onto the carbocation, which is good. We have a carbocation there now. This methyl moves over, and that should be it. Okay, let's check this out. Oh, and it wants you to show the resonance structure too. Alright. Well, that's not cool. So resonance is pretty easy. You want to be octet satisfied above all. So this is the preferred resonance structure this is the preferred resonance structure, even though it has a positive charge on oxygen. Usually we'd like to put a positive charge on carbon opposed to oxygen, but this is more preferred because everything is octet satisfied. So that should be what we want. Submit response. Correct. That was great. And well, they kind of screwed you over a little bit there with they just showed you what the resonance structure is, but they didn't tell you they wanted to provide curved arrows toward the resonance structure. I thought this was the end, and they were like, oh, this is what it can be. But good problem. If you approach it with a strategy in mind, a methodical way of doing this one, it's not too bad, I guess. It could be a lot worse, let's say that. So I hope this was helpful, and I'll catch you next time. Thanks.